it's funny. Have you ever just stood in your kitchen and listened? That low hum from the fridge, or the whir of the washing machine, the spin of a fan. That sound, that motion, it's all powered by one of the most important inventions you probably never think about, the electric motor. They are literally the invisible engines of our world, and we're going to pull back the curtain and see exactly how they work. So here's how we're going to break it all down. First, we'll look at the one hidden force that makes it all possible. Then we'll see how you actually build a motor from that force. We'll get into the genius behind the most common motor design on the planet, the squirrel cage. Then a really important part, the efficiency equation. And finally, we'll see how we make these things smarter, faster, and stronger with modern controls. All right, let's dive right in. We have to start at the very beginning with a single fundamental scientific principle that is the bedrock for every single electric motor ever made. I mean, this is the big question, right? It seems almost magical. How do you take electricity, something you can't even see, flowing through a simple wire, and turn it into real, physical, spinning motion? Well, it's not magic. It's just really, really cool physics. And here it is. This is the secret sauce, the core concept. According to the textbook Electric Motors and Drives, it all boils down to something called the electromagnetic force. This is the aha moment. All it means is this. If you take a wire with electricity flowing through it and put it inside a magnetic field, it gets pushed. A real physical force appears out of nowhere, and that push is everything. Think of it like a super simple 3-step recipe for motion. Step 1, you need a magnetic field, like from a regular magnet. Step 2, you stick a wire inside that field and you run some current through it. And bam, step 3, a force is generated and that wire wants to move. That simple little push is the birth of every electric motor. Okay, so we can create a little push on a wire. Big deal, right? Well, how do we get from that one-time push to continuous, smooth, useful rotation that can actually do work? That's where we go from a science experiment to building a real machine. So it turns out every motor, whether it's tiny enough to make your phone vibrate or big enough to run a freight train, has two main characters in its story. First, you've got the stator. That's the part that stays still. It's stationary. Then you have the rotor, and as the name implies, that's the part that rotates. The stator makes the magnetic field, and the rotor is the part that gets pushed around by it and spins. Now, the stator's job is just brilliant. It's not just one big magnet. Instead, it's lined with coils of wire called windings. And here's the clever part. By sending electricity to these coils one after another in a perfect sequence, you create a magnetic field that spins around in a circle without a single part actually moving. It's an electronic rotation. This idea of a rotating magnetic field actually dates all the way back to 1824 from a guy named Francois Arago. So if the stator is creating this spinning magnetic dance, what's the rotor's job? It's simple. Chase it. Imagine holding a compass, and I start spinning a big magnet around you. The needle of your compass is going to desperately try to follow that magnet, right? That's exactly what the rotor does. It's in a constant, endless chase of the stator's rotating field, and that chase is what we call torque. This brings us to the king of all motors, the most common, most rugged, most widely used AC motor in the entire world, the induction motor. And the secret to its success is its incredibly clever rotor design. But wait a minute, there's a huge problem here, isn't there? The stator is plugged into the wall, it's getting power, but the rotor is just spinning in the middle. How do you get electricity into the rotor so it can create its own magnetic field to get pushed around? You can't just attach wires, they'd get tangled up instantly. This engineering puzzle is solved by one of the most elegant designs in history. And the answer is this thing. It's called a squirrel cage rotor. And yes, it's because it literally looks like a little exercise wheel for a squirrel. It's just a bunch of solid metal bars, usually aluminum or copper, all connected at the ends by 2 rings. That's it. It is dead simple, incredibly tough, and, most importantly, it has 0 direct electrical connections. No brushes, no contacts, nothing to wear out. It's just a masterpiece. So how on earth does it work with no wires? The answer is one word: induction. As the stator's rotating magnetic field sweeps past those metal bars on the rotor, it magically induces an electric current to flow in them. It's the same principle a transformer uses. Now, that brand new current flowing in the rotor creates its own magnetic field. And it's the interaction, the push and pull between the stator's field and the rotor's new field that creates the torque and makes the whole thing spin. It's completely wireless. It's pure physics. So we have this powerful, simple, rugged machine. It's amazing. But in the real world, where we have millions, maybe billions of these things running all the time, there's a huge consequence. And that brings us to a really surprising financial truth about electric motors. Get ready for this, because this number is pretty mind-blowing. This comes from the ABB Motor Guide. For a typical industrial motor, the price you pay to buy it is only 1 to 3% of its total lifetime cost. 1 to 3%. So where does the other 97+% come from? It's the electricity bill to run it. This one fact changes everything about how you should think about motors. Right, because energy is the real cost. Global standards were created to help people make smarter choices. This is the IEC 6003430-1 standard, and it gives us these international efficiency classes, or IE classes. It's a simple way to grade motors. Choosing a high-efficiency IE3 or an even better IE4 motor might cost a little more upfront, but it can save an absolute fortune in electricity costs over its life. It's a huge deal for both the bank account and the planet. Okay, so we've picked a super efficient motor. Awesome. But how do we actually control it? Because it turns out just flipping an on switch isn't always the smartest move. Modern electronics have given us much, much better ways to do it. When you just use a simple on switch, you're doing what's called a direct online start. And this is basically the electrical equivalent of flooring the gas pedal in first gear from a dead stop. You get this massive surge of electrical current, sometimes 6 to 8 times the normal amount, which puts a huge strain on the power grid and physically jolts the entire machine. And you can really see the difference here. On one side, you have that direct online start. It's a brute force approach, high currents, abrupt, and mechanically really stressful. On the other side, you have the modern solution, a variable speed drive or VSD. It's a piece of smart electronics that gently ramps up the power, giving you a smooth start with low currents and perfectly controlled torque. It's just a smarter, kinder way to get things moving. But a VSD is so much more than a soft starter. Its real superpower is being able to change the motor's speed on the fly. Why run a fan or a pump at 100% speed if 60% is all you need? By precisely matching the speed to the actual work required, VSDs can slash energy use, sometimes by more than half. They make the whole system smarter, more precise, and way, way more efficient. As we wrap things up, this simple quote from Electric Motors and Drives just hits the nail on the head. At the end of the day, a motor's physical size, how much iron and copper is in it, comes down to just one thing: how much twisting force or torque it needs to create. You need more torque, you need a bigger motor. It's that simple. It's the fundamental constraint that engineers are always working with. So, from a simple physical force to a rugged workhorse that powers our entire civilization, the electric motor's journey is just incredible. But the story isn't over. As we push forward into a future of electric cars, hyper-automation, and advanced robotics, this humble, brilliant invention is more important than it has ever been. So the real question is, what's the next challenge we're going to throw at it?